Microphone check. 1 2 1 2 1 2. Here we go. Live. Today we're gonna get a lesson from Brett, man. If you don't know who Brett is, Brett's a long-time member of this community. Brett's been teaching me LeetCode for over 3 years. Oh, Icy Black Deep is in the house first today. How you doing? What timing? Type Racer, dang, already? Res Pi, how you doing? JCast19 in the house. What do you mean, what timing? Icy Black Deep. Solbs, how you doing? Where's my thinking cap, man? I don't know. I don't have one. So, but hopefully we can learn about these dang fenwick trees today. Am I live? I mean, clearly people are chatting, but my OBS stats don't look too great right now. Hopefully it's all good. Got home and the stream is on. Well, you know it, man. 9 p.m. for sure. Layman's, how you doing? Welcome to the stream. All right, we're gonna type racer in a little bit. We gotta wait till some people get in here. We don't want to just do a type racer with a few people. You know, we need triple digits on that board. How are y'all doing, man? Are y'all ready for fenwick trees? We're gonna get a lesson from Professor Brett. Very excited, I think. I'm a little bit scared. Like, I don't know anything about fenwick trees. I didn't, you know, it's supposedly a very complicated topic. I'm afraid I'm gonna look like a fool trying to understand these fenwick trees. Is he doing voice call today? Yeah, we're gonna jump on voice. So we're gonna do that after I do the daily problem. And before we do the daily problem, we're gonna do a type racer. Yeah, so that's what's happening today. How many of you already know about fenwick trees? I only know the name. I don't actually know like how it's useful or what it solves or anything like that. Strike on, bro. Welcome to the party. Icy Black Deep, do you know like how to use fenwick trees and stuff? I mean, I imagine most people here don't know about fenwick trees. Nope. Dang. Icy Black Deep is also pretty good at algorithms, so I seen you solve some hard advent of codes. Even though you don't do LeetCode contests, I still think you're pretty strong. Alright, should we just jump into something? Oh, the real Raymond Jones. How are you doing, man? This is a little mini event. Brett's gonna teach us about fenwick trees. Isn't it similar to a segment tree? Whenever I hear fenwick trees, I usually hear segment trees also, but I don't even know the difference. Maybe you can save all these questions for Brett and he can answer them. Just chilling. I like that. Isn't it past your bedtime, man? Raxo Sabe in the house. How you doing, Raxo? Most advent of code doesn't take deep CS topics, man. I don't know if I agree with that, man. Advent of code is tough for at least. I don't know if it's. I've never actually tried beyond week 2 because I think I get burnt out, and it's like around the holidays, and that's like major chilling time. But from the looks of it, man, those problems aren't easy. That's for sure. All right, who's here for Type Racer? We had a Type Racer redemption at the beginning by ResPie. ResPie wants to race everybody. Hamza Kwaziz, how you doing? Welcome to the stream. All right, we're gonna start off with a Type Racer. And hello, YouTube, if anyone's in the YouTubes. Let me set some windows up. Type Racer, Type Racer, Type Racer. Let me hit the Type Racer Discord channel. Send it to the YouTubers. And send it to the Twitch people. All right, first race is a warm-up. Second race is a championship round. Then we're gonna do the daily problem real quick, and then we're gonna try and get Brett on the line. Are y'all ready? Ain't nobody at the racetrack, man. Lysander is here. Who is ResPie here, man? ResPie, redeem this. Let's go. Lysander Trades, how you doing? Is it just gonna be me and you, man? Let's go, let's go. All right, SM is here. All right, this is just the warm-up. Just a little warm-up, man. Let's see, get those fingers warmed up for these dang... Man, did they update the UI for Type Racer? Like, the way it moves the cursor, it looks a lot different, man. It looks like it's in 60 frames per second or something. This is just the warm-up, so if you're joining in now, it's not too late to be a part of the championship round. And if you want to be a Type Racer champ, this seems like a great race to participate in since not many people are here. That means I gotta perform really well in the championship round to make sure that there's at least triple digits on the board today. Here we go. Is that an upgrade or a downgrade? I mean, it looks nicer, but I think it's a little bit distracting. All right, Type Racer, man, come on, get in here. ResPie, where you at, man? I am disappointed ResPie isn't here. And why, man, my chat keeps like scrolling all the way down. It's all good. All right, here we go. Championship round. SM 97, dang. Here we go, here we go. I must defend the... Oh, Jesus Christ, man. It's so long. Ain't no triple digits coming right now. Oh, SM, you did it, man. You did it with the 100. Oh, I'm so happy. I was trying really hard to get triple digits, man. I'm so happy you got triple digits, even though you beat me. Um, I really hate to put double digits on my on my dang championship board. Congrats, SM. Have you won a championship before? Yeah, you won before. How many? How many have you won? Ooh, this is your second championship. Very nice, very nice. At exactly 100 WPMs. Man, in Rosis in the house, you just missed the type racer. Somebody redeemed a super early type racer. And they didn't even show up, man. Person who redeemed it didn't even show up on the type racer, at least. All right, it is the 13th. Dang, it's the 12th? Say the 13th? How is this the 12th, man? This must be the 11th. I must have messed up there. All right, SM123 at exactly 100 WPMs. Congrats. Very nice, very nice. Reaction Cutie, how's it going? Man, it's just 61, dang. I mean, it was a long, hard passage, man. All right, we got to do the daily problem. And then we got to get ready for fenwick trees. All right, let's see what the daily problem is all about. I don't even try anymore after 55. Man, what do you mean? You gotta keep on keeping on, man. All right, here we go. Here we go. Binary subarrays with sum. My pinkies are useless. Do you smell a DP problem on contest tomorrow? Tomorrow? There's a contest tomorrow? Or you mean this weekend? I'm not sure. I'm going to try and take the bi-weekly though. We'll see how that goes. Yeah, do I use my pinkies when I type? Yeah, my pinky press shift. I only use my left pinky, actually. Thought it was Friday. Man, what you been smoking in Rosis? You hanging out with Blaze Pascal too much. Contest. Oh, you thought today was Friday? Man. It ain't even Thursday, man. You're tripping. It's the stream melting my brain. Yeah, we got a long way till Friday, man. All right, here we go. Let me read this problem. Given a binary array nums, binary array, and an integer goal, return the number of non-empty subarrays with a sum goal. Subarrays are contiguous part of the array. All right, so I mean, I think I know how to solve this immediately. Skip Pharaoh, how you doing? Welcome to the party. Yeah, this problem seems pretty standard. I'd say it's basically prefix sum, and I've been seeing prefix sum. So man, in Rosis, if you ask me what do I think is coming on the contest, I'd say prefix sums, man, because what did we get? This one was a prefix sum on Tuesday. Today's a prefix sum on Thursday. Maybe they're setting us up for some prefix sums this weekend. All right, let me see if I can actually solve this dang thing though. So, let me try and explain as I go. So we have this array. I guess this is like prefix sums and 2 pointers. So I have my prefix sum as a unordered hash map, basically. And it's gonna count like the running sums and how many times those sums appear. So we start off with 0 appearing once, because the sum is 0 before we iterate through the array. So that's like our starting point. And then we just get the sum as we go. So there's a sum of 1 there. And then there's another sum of 1 because this subarray sum is 1. So there's 2 1s. Then it goes to 2. So 2 appears once. Or well, let me show you how it goes as I'm doing it. Q Ultimus in the house. Glad to see you around, Q. Alright, so it's gonna be like our target is like our sum minus our goal, I think. Yeah. So in this case, we are here. Let me try and zoom in a little bit more on this, and I'll link this problem. Alright, so check me out. We're here at index 0. We add this to our sum. So our sum now becomes 1. And then our target, this is Ryan from YouTube. What's happening, Ryan? How are you doing, my friend? Welcome to the party. Right now I'm doing the daily problem. Then we're gonna jump into some crazy stuff. Where was I? Yeah, our sum is 1, our goal is 2, so our target is -1. And then do we see sum in our prefix sum of -1? No, we don't. So then our answer is currently 0. And then we move on to the next one. The sum is still 1, and then our target is the same, -1. Do we see a target of -1 in here? Nah, so our answer is still 0. Then we go on to the next index. Now we can increment our sum because 1 plus 1 is 2. And then now our target changes. Our target is now, the sum is 2 minus the thing is 2, which is, so our target is 0. So we look in our prefix. Oh, I didn't even add the things in our prefix sum. 2 sums of 1. So we're looking for a target of 0. We look in our prefix sums hash map. We see, oh, we do have a sum of 0, and there's one of them. So basically, this has a sum of 2. So we add that to the answer. Answer is now 1. Then we go to the next thing. Our sum is still 2. So now we have 2 sums of 2 in the prefix sum. Our goal is, or our target is 0. We have the same one thing of 0 in there. So now we've found 2 subarrays with sum 0, and it's this one right here, and then it's this one right here. And then we move to the next one. So we increment our sum. Our sum is now 3. This whole thing is 3, right? Did I add that thing to the thing? Yeah. So our target changes. Our target is now 3 minus 2, and that's 1. We look in our prefix sums. We see we do have a sum of 1, and it appears 2 times. So we add those 2 things to the answer, and we get 4, and boom, that is the answer. It's a little quick prefix sums and 2-pointer style technique. Let me code that up fully for y'all. So we need the answer. We have our sum. Let's make our prefix sums thing. And then let's add a 0 initially. That appears 1 time. And that just represents the sum before we process any elements in the array. It's at 0 in the beginning. And then now, I guess we can just iterate through nums. and we'll be like, our target is equal to our sum minus our goal. And I suppose we should like, we should check if, I don't know, Icy Black Deep always says I should just find it once, my iterator. So if we'll find that target, and then we'll be like, if it's found, then how does that work, man? I'm trying to be too fancy. Right? Does this look right? So if this is our iterator to find that target in this hash map, and then this says if we've found it, then we just add the second value in the pair, which is our how many times that sum of pairs, and then now we have to add that to the thing, and there we go. I think that should be it, man. Should we make a bet? See if this passes. On that, from YouTube, how does trying to solve these problems not make me mad? Well, I think first of all, I have great control over my emotions. And second of all, I think these problems are kind of fun these days. But for sure in the beginning, I got frustrated a lot. Pets, hello world. Thank you very much for the raid. What's happening, Pat? Did you solve that monkeys problem, man? That well bet money on? I wasn't there to see the final results. Should I bet or should I just submit this? We solved it with help. Did you get wrong submissions? Oh man, wait. My answer doesn't even work. How am I gonna get 0 here? Did I mess up? For sure I messed up. Because it's wrong. Oh, you know what I didn't do? I didn't I didn't add to my sum, man. Oh, Brett is in the house. What's happening, Brett? Yeah, I forgot to update my sum. We should have made a bet there. I'm sure lots of people would have gotten that wrong, maybe. All right, so there's a daily problem, prefix sums. This is the second prefix sums problem this week. So maybe y'all should practice some prefix sums before this weekend. All right, are y'all ready for Fenwick trees? When is this approach used? With the map? I'm not, what can I say? I think, I don't know. I guess whenever they ask like how many subarrays equals this sum, it's pretty much like a two-sum type of problem. It's like counting. It's, I don't know how to tell like if there's a surefire way to tell you when you should use prefix sums with a hash map instead of like just using the regular array. I think it really depends on the problem, but I think for sure when they're asking you like how many subarrays equals this target, then maybe the hash map might be useful. Is there a way to do yesterday's daily without brute force? I don't remember what yesterday's daily was, but I'm sure there is. Pivot integer? This one you're talking about? Here's my solution. So I get the sum of the whole array, and then I iterate through, and I have the left sum, and then as I'm iterating through, I'm adding to the left sum, and I'm taking away from like the right sum, and then once they're equal, we found like a pivot. So I don't think this is brute force. I think this is optimized because it's ON. There's a math formula for yesterday's problem. It's crazy. Answer is square roots. Dang. I didn't even know that. So I suppose my solution isn't even fully optimized because you can get an O1 solution there. Did you give anyone a super secret gift? Nobody has gotten 1,000,000 channel points yet, but Q Ultimus is on his way if he stops losing bets. All right. Are y'all ready? Y'all ready for Brett? How should we do this? Should I get Brett on the line right now? Learn about these fenwick trees. I forget which problem we're trying to do. Should I get my headphones out? I haven't worn these headphones in a long time on stream. All right. Y'all ready to bring in Brett? Am I into metal music? I am. I don't even know metal music that well. So no, I don't think I am. When ASMR stream, I don't know if that's coming. All right. Let's bring in Brett. Are y'all ready for it? About to call him right now. Can you hear me, Brett? Is Brett on the line? I can't hear anything. Maybe we're having some technical difficulties here. Uh-oh. Maybe we should have tested this out before going live. I guess we'll wait. I thought you're into metal because of the hair. Oh, wait.
Should I make my...
All right, I can hear Brett. Can y'all hear Brett? I can hear you, Brett. No. Got to turn up the volume. All right. Say something.
Hello.
All right. His voice is super low, they say.
What about now?
What about now? Let me turn you up on my side too. He's at 20%. Oh, wait. All right, try again.
Can you hear me now?
I can hear you, but can chat hear you?
Can chat hear me is the good question.
Yeah. All right, I got your volume up at 200% in Discord.
That's a lot of percent.
Yeah. All right, they're saying they can hear you.
Still a bit low. I have my input volume at max on Discord. Odd. Do you want to restart? I'm not sure if restarting the call helps at all. I don't know.
Yeah. Maybe let's ride with it. Let me turn on. It's not too bad, they say. Yeah, my OBS settings is at max. Maybe I can add like some filter to like bump up my volume even more.
Do you have you messed it all with the settings in Discord?
Yeah, I put you at 200% volume on Discord.
Yeah. And I hear you fine in my headphones, yeah.
All right, I got this plan. I'm gonna add some gain.
Ooh.
Keep talking.
I will continue to talk.
All right, I've added I've added some gain, maybe.
What about now? But does it sound good still, or is it just loud?
I mean, it sounds okay to me right now. Gets louder, it's fine.
That's
All right, people are
all
saying
right. Wow.
we're good to go.
Fine. Fine. We'll stay with a fine. So
All right, all right.
so the goal for today is to immediately become a LeetCode guardian, obviously.
All right, so with this trick, I might become a LeetCode guardian, is what you're saying.
Okay, so I think we'll talk about advanced data structures, and fenwick trees will be on there. And so the idea for today is we'll go over like maybe 2 data structures. Using them is going to be relatively easy. So there's going to be problems that you currently cannot solve that will become easy to solve once you know these data structures.
Okay.
Now, if you actually wanted to implement these data structures, that would not be easy. But I mean, it's not easy to implement standard map or standard set either.
Right.
So
I get what you're saying.
right. But maybe we'll spend a few moments on the fenwick tree trying to look at why this short amount of code does seem something that seems a little impressive. Because you'll look at it and it'll be very short code, but then it'll be like, wait a second, why does this even work?
All right.
Okay. So maybe to start off, so we're going to knock off 2 data structures today. So
Ooh.
to start,
2 of them.
well, 2 of them. So the plan is this. I'll lay out the plan. The plan would be I'll tell you what an order statistic tree is, because people will often say, "Oh, using a fenwick tree for that problem, why don't you use an order statistics tree?" They'll be and vice versa. So I'll tell you what those are too. Again, it'll take like a few minutes and it'll be very easy to use. And we'll use both order statistics trees and fenwick trees to solve the problem. Again, it'll be pretty easy to understand what they do. The only thing that's rough about the order statistics tree is that you have to have this nasty 3 lines of import at the top of your C++ file.
Oh, right. Yeah, I think BetSimp was talking about that the
Once you
last
get
stream.
the nasty import done, you're fine. It's easy to understand how to use it.
Right.
You wouldn't want to implement it on your own. It's not impossible. It could be like a long homework assignment, but I mean, it's you don't want to do it.
Yeah, I definitely don't want to do it.
I'll also tell you about fenwick trees, obviously. It's also going to be really easy to understand what they do. It's even thematic with the problem you did today and what you said is going to be on the competition. It's related to prefix sums. Fenwick trees are just about prefix sums.
Interesting.
Yes. So it's a perfect day.
Perfect day. I can't imagine a more perfect day.
Yeah. It's short code and it's cool, but the code is a bit tricky. But I think the concept is nice, and you like prefix sums, so it's going to be great.
Okay.
What we are not going to cover, which is also related to both of these, is segment trees. They're also a cool data structure, not that hard, just not today.
Okay, not today. Not
but
today.
A future day, we can talk about segment trees, and you'll see it also, once you just paste this block of segment tree implementation at the top of your code, would immediately open the door to a bunch of problems you can't currently solve.
Okay. Quick question, Brett. Do you copy and paste in competitions?
So to be clear, at LeetCode, I've competed 10 times total, and I have not copied and pasted in a single one.
Okay, but in previous competitions...
did I ever copy paste? I don't think I ever copy pasted. And then when I did ICPC back a long time ago, you weren't allowed to copy paste. I think back then you could like bring a printout of stuff, but not actual. Yeah.
Okay.
So I don't copy paste. I even like 2 or 3, like once or twice when I was doing the LeetCode competition, I even hand coded the union find data structure like on the spot. So I was not copy pasting at all. Yeah.
That's hardcore stuff.
Yeah, but if you wanted to be fast, you would just have like a few files of these things ready to go, and you just bam, and then you're done, right?
Yeah.
You're racing.
All right.
Okay.
All right.
Okay. And then what we will do is we will go over some hard problems, quote unquote hard problems, and then you're going to see that they're easy. So you're going to get a bunch of problems solved in LeetCode today.
Oh, my number is going up.
Yes. So this is going to be interactive. I don't like to talk a lot in a row when I teach. So problem number 1. Go to LeetCode number 315.
315. Here we go.
Yeah.
All right. Is this format good? Do you need to like draw things?
I've prepared in such a way that I want you to do everything.
All right. Great. It's gonna be exciting.
Yes. Okay, so I want you to think about this problem for a few minutes, and then we're going to get into how to solve it.
All right, let me read it really quick. Count of smaller numbers after self. Given an integer array nums, return an integer array counts where counts I is the number of smaller elements to the right of nums I. I'm familiar with this problem, and I know anytime I see these types of problems, I just immediately give up because I know it's like fenwick trees and stuff, or
What's going to be
segment
crazy is
trees.
that my hope is that in the future you will see this problem and be like, wow, this is one of the easy ones.
Okay, so let me
Okay,
try to give it some thoughts like I usually
sure,
do.
yes. So give it, yeah, exactly. Think, do your comment thing. Think
All
about the
right.
problem, try to understand it.
So we have some nums, and then we need to find out how many smaller elements are on the right. Um, what would I'd think maybe I'd go through my checklist. Maybe I'd check something with like stacks or queues, or what else would I normally do? Yeah, I think maybe some type of monotonic stack. But then I think I've been down this path before, and like the problem is sometimes you pop off more than you need to, and then it's hard to get the numbers back. I don't know if even know if I'm
Sure.
making sense, but
So, so let's think of a magical data structure that if we had it would solve this problem like instantly. So suppose you had a data structure where you could ask it, of the numbers I've inserted thus far, how many are less than X? And you
oh yeah, I know this
if you,
data structure. It's called a sorted list in Python.
okay, so you have the sorted list in Python. We're going to do the C++ one, which is going to
Yeah,
be a bit faster than the has faster guarantees than the sorted list in Python. Um, and so you're not gonna have to use Python for this. But yes, the Python users at home might want to use a sorted list for
right.
solving this problem.
So I guess if we had this magical data structure, I'd probably start iterating from the right side of the array, going
Mhm.
left, adding numbers in, and maybe like doing some type of binary search to figure out where the current element is that we need to find elements less than it, and like take a distance of that pointer to the beginning to find out like how many
Great.
things are
And if
before it.
we yes, and if we tried to do that with a regular vector, where we just are maintaining a sorted vector, that doesn't work either because every time we try to insert into the sorted vector, that would be really slow.
Yeah,
So
that's like
we need a
on.
data structure we can exactly ON, like quick reset. So we need a data structure we can insert into cheaply and also cheaply ask how many values are less than X.
Right.
Okay. So
Makes sense.
right. So what is this magical data structure? So let's think about this for a moment before. So I maybe we can take. I can give you a choice here. Do you want to just solve the problem first, or you want to understand the data structure we're about to use?
I want to understand it. I think I
Okay.
really enjoy understanding things before I use them.
Okay. So I'm pasting something into Discord. This is a Wikipedia link.
Oh man, Wikipedia.
Just that should be an image. Okay. So this is a regular binary search tree.
Okay.
Okay. So as you can see, if you wanted to search for something in this tree, everything to the left of a node is less, everything to the right is bigger.
All right.
Okay. And you usually don't see trees like this, but you can even have trees that have duplicate nodes, where maybe everything to the left is like, let's say, less than or equal, and everything to the right is strictly greater.
I see. Right.
You could even have that. But we'll pause on that for a moment.
Okay.
Okay. So the first thing to note is that when you search in a binary search tree, the amount of time it takes to find something, at worst, is the height of the tree.
Right. That makes sense.
So the magic that standard map and standard set are doing underneath, and standard multi-set and whatnot, underneath, is they're maintaining a tree, and every time you add to it, they're doing operations that keep it pretty balanced, so it doesn't turn into a long right list.
Yeah. So,
So that's kind
so
of amazing that they do that.
Right, but the problem I had previously with like say a multiset is when I tried to find how many elements are smaller, that calculation is O(n) time,
Correct.
which is bad.
So even in this binary search tree we're looking at, is there something we could do that would make that question you just asked fast? And here is the magic. Here is the magic of order statistics trees, which isn't that magical. What if in each node we put the size of the subtree rooted at that node? So let's see what it would
Oh
be in this
yeah.
tree. So in
Wait,
this tree,
let
like
me bring up
the
my
six.
pen. 1 second.
Well, I'm about to give you another picture in a second. So
Oh, okay.
I think I. Oh, I know. I'm about to. Here, let me give you a picture of a different tree that has some numbers in it. Okay, can you put this image online on your? I just pasted a slide to you that I found online.
All right, let's see.
Great. Okay, so over here we have a new binary search tree. The values in the tree are letters. So everything to the left of M is going to be lower letters, and everything to the right of M is going to be bigger letters.
Okay. And the 8 is the size of the subtree
Rooted at that tree.
rooted at that tree, right?
Okay, so now let's do some examples. So let's suppose you wanted to know how many elements in the tree are less than H.
How many elements are less than H?
Okay, so
Okay.
let's see what happens. Forgetting the fact that there's numbers in the tree, how would we find H? We'd start at M, we'd go left and then right, then the right to find H, right?
Yeah, so
Okay.
H is less than M, so we go left. H is greater than C, so we go right. H is greater than F, so we go right.
Okay. So every time you go right, you are now skipping a bunch of elements to the left that were ahead of you.
Every time we go right.
So when we go from C to F, there's a bunch of elements that are earlier than F that we just skipped that we'd want to keep track of if we want to know how many values are less than H.
Right.
So how do you figure that out? When you
guess,
go to F, which is right, you know that the subtree at C had 5 in it,
yeah.
and F only has 3 in it. So you're missing 2.
So you take the difference.
And that's
Yeah.
it. So you've already accumulated 2. And then when you go right again, you're accumulating another 2.
I
And then
see.
the answer is 4.
I
so
see.
in one pass down the tree, you immediately know how many values are less than H.
Okay, that makes sense, actually. I see how that works.
And you can even do it for values not in the tree. You just find them and then they fall off because there's no leaf that corresponds to that letter. So if we wanted to find G, for instance, you could do the same thing and you can find how many values are less than G.
Man, who thought about this?
So this is actually pretty easy. It's the problem though, which makes it hard, is the balancing the binary tree is hard. And not only that, as you balance the tree, you have to constantly update the numbers in the nodes.
Yeah, that seems very difficult.
Yeah, so fortunately, someone did this for us. And I'm going to give you like the 3 lines of code. You just have to paste at the top of your file, and then we're going to kill this problem.
Okay.
So you just have to have, now this is not like a pasted data structure. This is just something that comes with GNU for free. So I am now going to give you the code to paste, and I'll give it to everyone in chat too. Here, I'm putting it in chat. There you go.
Is that how you pronounce that? GNU?
I don't know. It's an acronym. GNU is not Unix, and the G stands for GNU again.
All right. I always thought it was like silent or silent G.
Oh, a new? Yeah, it might be a new.
Maybe.
I mean, like, yeah, the animal? Yes. Okay, so if you paste those lines at the top of your code,
All right.
so it's a long line over there. But what I've given you is a data structure called an order multiset that just came with all this new PBDS, policy-based data structures.
Yeah, I think. Is this what BetSim also had yesterday?
I believe so.
Yeah, yeah.
Yeah. Right. So you got that thing. Exactly right. Okay, so now we are going to try and now you're going to be able to use this. So you can insert into it just like a multiset.
Okay.
And then when you want to get to, when you get to the point where you need to find everything that's strictly less than a value, ask me, I will tell you that function.
All right.
So,
So,
so solve the problem. I'm going to let you take
oh
the wheel, and
man.
then a
All right.
problem that you previously would always skip.
Yeah, I've thought about this. I've tried this a few times and I know I can't solve it, but maybe with this new data structure I can.
The
So,
power.
all right.
So it's a template. So the way I just, because the way I defined it, it just like a vector, it has a power
Yeah,
template
yeah.
parameter.
So I'll be like ordered multiset int OMS. I'm just call it that. And then
Sure.
I'll iterate from the right side to the left side. First, I guess I want to. All right, I need your help. I need to figure out the current number. So if this is my current number, nums I need to figure out like how many numbers are smaller than this target or this current number in the multiset. So
Right. So that is OMS dot order of key.
with like things like that,
Order underscore of underscore key.
order of key there. And this will give me the index at that key, like an integer index.
It will give you the number of elements strictly
Oh,
less than that key.
okay.
It's exactly what you want.
All right, let's see.
I
And then
think, yeah, exactly. You need to set up an answer.
all right, so here's oh wait, I'm not done.
Don't forget to insert.
Yeah. So you're saying this is all I need to know to solve
You're
so many
done.
hard problems.
Yeah, so I just opened the door to a zillion problems. We're done.
Are you saying if I submit this, it's gonna work?
Well, you're the one who likes
No.
gambling on submitting.
No, that's crazy, man. That's like a easy
What was that?
problem. That
So
is,
this is this problem with these few lines of code is the one that scared you. You had nightmares. Now
yeah.
that's it.
Well, now I know how they actually work under the hood too, so I don't feel so cheap in just using them like this.
This is a hard, by the way.
Yeah.
You
Yeah, this
know,
is
yeah.
crazy. Chat is saying it's crazy too. This is the power
This
of
problem is
data structures.
42% acceptance rate.
Yeah, all you gotta know is ordered multiset thing or whatever it's called. How do you say this? Or tree order statistics node
Well,
or whatever.
that's the crazy language of how this policy-based data structure works. It's called an order statistics tree. And
Yeah.
basically what that means is it's storing extra metadata, extra statistics in the nodes to help you do
Oh,
things.
that's what the statistics means in that thing.
Yeah.
I was wondering, like, it's a
Yeah.
crazy name. Makes sense.
Is this available in Java? I haven't coded in Java in a while, so I haven't looked to see if it is.
Interesting. I mean, it must be available in some ways in Java. Well, maybe not in the standard
Sure, you can
library.
find. There's got to be people who compete in Java who if you look at
Yeah,
their solutions.
yeah, for sure. There's top Java people out there.
Yeah, so you can probably go look through the solutions that Java people are using and see if anyone has something like this. Although maybe they use the fenwick tree.
Oh, yeah, man, this is crazy. It's even starred
It's
problems that I
starting.
can't do.
You know where? So that's where you used to be. Problems you can't do
Yeah, well, I gotta
that are all
remove it
new.
now. Remove, yeah. I can do this now. All right.
Mind blown.
Yeah, this is good stuff.
All right. So now that I've unlocked a bunch of problems for you, And yes, the first step is being able to use it on the easy ones. The second step is seeing, oh, now that I use this, can I use this at the end of a bunch of other logic that you figured out? And you'll get better and better at using them. But for now, a bunch of easy problems that are marked as hard you could solve.
Okay.
Okay.
I like that.
Bam. Okay, so that's the end of part 1. We have done order statistics trees.
Easy work.
That was okay. So now we get
to... numbers is here. I'm sorry to interrupt, but what's happening, numbers? Long time no see.
He hasn't been here in a while, right?
Yeah, he's in the UK, I think. Crazy time zones, or maybe he's back at home now for spring break or something.
He heard you were solving a problem with order statistics trees and had to be here.
Ooh, 2 a.m. Well, thanks for showing up, numbers. Bert's giving us a crazy lesson. All right. Sorry.
All right.
Continue.
Part 2. We're now going to look at fenwick trees. And as I said earlier, just to put us in the mindset of fenwick trees, it's just like prefix sums. Before I give you the next problem to jump into, let's think for a moment of why do we do prefix sums?
Okay, prefix sums for sure is to quickly calculate the sum of a subarray in O1 time.
Correct. It's range, or sometimes called range or subarray sums. Okay. Now that's great. So you would take an array, compute the prefix sums, and then you can do a range sum and as much as you want. So now I'm going to throw a curveball at you.
Uh-oh.
What if I'm also allowed to change the elements of the array dynamically?
Oh, man.
That makes it much harder because it will break all the prefix sums after it.
And then you have to like recalculate the whole thing.
Right. Okay. So that's the problem that fenwick trees solve. How do you update the elements of the array but still quickly compute range sums?
I mean, it must be something like the same thing that the ordered statistics tree thing does, where it has
very
metadata.
Different.
No, very different.
The answer is going to be crazy.
All right, I'm not even going to try and guess. I'm not going to try and pretend I could come
up
with it.
I would have guesses about tree stuff, but I would not have immediately guessed fenwick tree, what it's doing. I should also say at this moment that this would also be a moment where we could solve this kind of problem using a segment tree. But we're not going to talk about segment trees today, so I'm going to stop. Well, I'm going to resist the urge.
All right, wait, before we leave the segment tree topic, quick question that somebody asked earlier. What's the difference between a fenwick tree and a segment tree? Is that an easy question to answer?
So a segment tree is actually, some people use the word segment tree different ways, but a segment tree, the one I'm talking about, is it's basically, you can imagine a tree where the leaves are the elements of the array, and then to each pair of leaves, you put an interval of size 2, which represents like the first two elements subarray, then the 3 and 4, then the 5 and 6, and the 7 and 8, and so on. And then those have parents that are the first 4 elements. So you're having these subarrays as nodes in the tree. And then you can use that to pre-compute like range sums or range maxes or range mins or a lot of other range stuff for each node, and use those to quickly in log n time solve range sum queries, range max, range min, and you can also, using the tree structure, update the tree quickly. But that is just another topic. You'll see that what we're going to do today is a tree, but it's weirder.
So the question is hard to answer. Got it. I don't even understand what you just said, but let's move on.
Yeah. Move on. It's not that bad, but it does take work to implement all the operations, the insert, the update, I don't want to make it sound like it's the hardest data structure ever, but at the same time, it's work. And the thing we're going to have today is going to have short code, and it's going to look a little impenetrable, and then we're going to dissect it because you want to understand how it works.
Okay, let's do this.
Okay, so go to problem 307.
307. Oops.
And I think I also agree with numbers
query.
that if you have a segment tree implementation ready to go, you'll never really need to use fenwick trees again. but fenwick trees are still an interesting idea.
Okay. Segment trees are strictly more powerful. Got it. But we got to work our way up to segment trees, maybe.
I think what it is after today, you won't say, I don't know what a fenwick tree is. But
Okay.
once you really learn segment trees, you might never look at a fenwick tree again.
All right. Well, numbers is here to try and remember what fenwick trees are. So.
There you go. The novelty of it, at
Yeah.
least, brings in the crowds. Yeah. Okay. So this problem is asking. So read the problem, and I'll let you take a look, and then we're going to solve it.
All right. Range sum query mutable. Given an integer array nums, handle multiple queries of the following types. Number 1, update the value of an element in nums. Number 2 is calculate the sum of the elements of nums between indices left and right inclusive. And we implement this class where the constructor takes in an array of numbers, and we have a method called update that takes an index and a value, and it updates the value at that index to be that value. And then another function that returns an integer called sumRange that takes in two parameters, left and right, and it returns the sum of the elements of nums between indices left and right inclusive. I see how this is gonna be. Wait, why is this a medium? I guess we'll find out.
So, well, I didn't take a look at what the success rate is on this one.
40%.
Not great. Okay. So, all right. So you agree that if they never had update, this was an easy problem, and you just use a prefix sum.
Right. Maybe I'd say medium problem, because I think prefix sums is a medium technique in my opinion. But yeah, easy medium.
Okay.
No,
sorry, quote unquote easy, relatively easy.
Right.
Right.
A standard
Because
problem.
then you just sum range, but the updates are screwing us up here. Okay.
Yeah.
Right. So now I'm going to give you code to paste. And this is code I just coded up today, and it will be the implementation of a fenwick tree. So hopefully that's a link to a fenwick tree implementation.
All right, let's see.
So you just paste this at the top of your code. For now, I don't want to look at the code. I just want to paste it.
All right, I'm not
and
looking.
Then we're going to look at it. Don't worry. I promise you we will look at it. But for now, we're just pasting it. So just paste at the top.
I'm not looking. There we go.
Okay. So, now I'm going to lie. I lied to you. We are going to look for a second. So just look at the constructors. We're just looking at the methods it has. So it has a constructor. I gave it one that takes just that takes a size and makes them all 0. I also have one that takes a begin and end if you want to initialize it to. I was being nice.
Yeah, cool.
Give you a begin and end. And then it has a method prefix sum.
Okay.
It has a method update, and it has a method set. Update means increment that index, and set means set it. Set just calls update, but yeah. We'll see in a bit that update's a little more natural in terms of the coding. That's why there isn't update at all, why there isn't just set. But okay. So anyways, now that we have this fenwick tree and we see the methods.
Yeah.
Now let's just use it to make our. So you're just gonna make you're just gonna use the fenwick tree to make the solve number.
All right. Let's try. So I guess a fenwick tree of ints, maybe.
Yep. Sure.
I'm gonna
Sounds
call
good
it
to me.
FWT.
Sure. I think I usually call them FT. But yeah,
FT.
Fenwick tree.
Let's go with FT.
Yeah.
And then it's a certain size, but we also have these iterators that we can send it. So I'm guessing we can just send in nums begin, nums end to the.
That's right. And are you going to use the constructor initialization list, or you don't do that? The colon thingy?
Oh man, I don't know that off the top of my head. Is it like
FT, and then you just put the arguments in there. Yeah, that's it. You do know it.
Yeah, I don't know. I'm not confident enough to do it off the top of my head. Every time I have to do this at work, I have to like reference my old code.
Right. So because otherwise you want to construct it. You actually want to call the constructor while you're constructing the object. Yeah.
Right.
Okay. Good. So that's it.
That's it. So
Now you
now,
okay. So an update. Yeah,
I mean, do
that's
I
this.
just copy index and wait,
So the
increment
update function,
is
it's kind of named a little differently. I think the set is what they're calling
right.
update.
So the
Yeah,
index and the value. Oh, I see. So you get the how much you increment
and then I
by
plug
what
that in.
was there, the difference. I see.
Yeah,
So you're saying we just call fenwick tree set index
index value.
value, and then we just return prefix sum? No.
Yeah, ft.prefix sum right. Yeah,
Oh, and then minus left? Or do we have to worry about the plus minus one thing
you
with
do
this
left
also?
-1 because you always want to not include. Yeah, exactly.
Wait, let's see what it's called. Prefix sum. Are you a fan of camel case?
So I do a lot of Python coding, and then I always have to use snake case. And then
Yeah.
whenever I do C++, I always use camel case. Yeah, same
And
for
you're
Java.
saying this is it? That's.
That's the hope.
Let's see.
3 lines of code after the pasting.
um, that is insane. I mean, there's a lot of code here. Not too much though.
Yeah, he
Oh, numbers
numbers
found a
pointed out that
bug.
I forgot to template my update and set, which is correct. I should have.
Oh, right.
Yeah,
With the
that's
values.
easily.
Oh,
Yeah, you should
yeah.
change the int
To
for the
T.
val to be t. Yeah,
Yeah.
that was. I literally like typed this up a few minutes ago. So
Man,
yeah,
numbers is very sharp. Everybody knows that though.
not a surprise that he would catch it. Yes. So yeah, so then you could use so this is there's a Fenwick tree. Okay, we're making progress.
All right.
Okay, so now there's 2 remaining things to this lesson, and then we're all done. Okay, the first is how can you use a Fenwick tree to solve the problem. So there's how do you use Fenwick trees? This problem is kind of a cheat because this problem is basically implement a Fenwick tree.
Yeah.
So the real question is, can you use a Fenwick tree for any other kind of problem that's other than implement a Fenwick tree? And so the first thing
We'll
we're going to do
see.
is solve the problem you solved before 315 using a Fenwick tree.
Oh man, that sounds doable, but we'll see.
And the last thing we'll do is understand what the crazy code does.
All right, 315. Here we go.
Back to, and you're going to recognize it because you just solved it.
All right, let's take the template Fenwick tree
Yep.
and let's get rid of this.
Yeah, we don't
And
need that anymore.
we'll start over now. Fenwick
The
trees.
much shorter include that we could have done. Yes.
Man, how
And
did-
also, just to address the thing in chat, I made, not accidentally, I intentionally made it the longer code because I wanted it to be nicer to use. I thought you'd appreciate it being a nicer to use one than a shorter one. There is a version I think I remember coding up like years ago that was really short, but it didn't
hard
have,
to
it had
understand.
less code in it. Yeah. And for
Right.
example, I also made it nice that it has a set function in it for you. Sometimes they don't put set in there and you have to maintain the array yourself. Yeah. I made it nicer as opposed to shorter. Okay. So but getting to the point, how would you solve this problem?
Oh man, this is a tough problem. You put me on the spot, Brett. I am not sure. Let me try and think. So how do we update things here? Like,
So the trick is, yeah, how do we use
Like,
prefix sums to
yeah,
solve this
prefix
problem?
sums. So maybe the first thing I would do is to just calculate the prefix sums and see how it changes as we go. So this is like 7, 6, and then
Well, so I should actually let you know one thing that we're going to do. So it's important for this problem to use a Fenwick tree that the size of the numbers in the array isn't that big.
come again? A Fenwick
So-
tree.
So
Oh,
the
like
Fenwick
the-
tree we're going to make is actually going to be of size the maximum element in the tree, plus one, whatever.
Oh, so like not 4 elements, but 7
Seven elements.
elements.
Right. Because we're going to start putting one in the spot of that number. So that way, suppose you're going right to left, okay? And you put a 1 in the 1 plus spot, and then you put a 1 in the 6 spot.
I'm
And then
lost.
you do the
But
so,
all right.
so let's make imagine we have an array, a fenwick tree array, right? That's going to have 7 spots, yeah, up to 6, so 0 through 7, 0 through 6 rather.
Okay.
Okay. Exactly. Okay. And now we'll do your algorithm going right to left. Okay. So initially all the entries have 0 in them.
I'll just keep those as indices or something.
Yeah. Okay. So initially all 0. So let's say we've already added 1 to it. And to add 1 to it, we're just going to increment spot 1. Exactly.
Like by
And then
1.
we add 6 to it. And we'll increment 6 by 1. Okay. And now suppose we're midway through the algorithm and we're at 2. And you wanted to know how many elements are less than 2.
I see.
How would you do that?
I see. Prefix sums of 2 to 0.
At starting at 2.
Yeah.
Prefix sums less than 2. So you do 2 minus 1.
Interesting.
Right?
It's so obvious now that you paint it out for me, but that's pretty cool. I don't think I'd have thought about that.
So now let's just code it up, and then I expect the code to be quite short.
All right.
You got this.
Let me try, man. Let me try. So we got the fenwick tree of size. Well, we have to find the max.
Don't forget the template primer.
Oh, right. Is it max elements?
Yeah, there is one, and you have to dereference it.
Yeah, so we needed max element plus 1. And then, so this is going to initiate or construct a fenwick tree with all zeros in there of size n.
Yep, exactly. That's
And
what we want.
then now you're saying we go from left to right or right to left, just
Right to
like
left,
we
just
did
like
before.
Oh, actually, I think we need one thing to be careful of, and maybe I should have checked this. Look, if you look a little lower, can the elements be negative?
Oh, so
So
now
we
we
should-
have to pad it or something.
So yeah, so we'll take the min and the max, and then we'll
Add the
add
min
the
as a
min to
pad.
all the elements. Yeah.
All right. Well, maybe I should just. Is there like a min and max, or should I
Yes,
just?
there is. There's a min, but you can just do it as 2 calls if you like.
Yeah,
But
I'll just be
you want-
lazy today.
Yes, there is a min max element that gives you 2 iterators, but that's not the important part of this problem.
Yeah.
Yes.
So
Okay.
we got the min and the max, and then this is gonna be that.
Max
me
minus
think.
min plus 1. Yeah. Oh, sorry.
Wait. So
Yeah.
if do I have to? Let me think. So if the min is positive, does that mean anything to us, or we only care if
If
it's
min
negative?
is positive, it even shrinks the amount of values we
Oh,
get.
so that's why you're saying max minus min plus 1.
Plus 1. Yeah.
Interesting.
Or if you like, that's a formula you can keep in your mind, which is if you ever have an inclusive range between A and B minus A plus 1 is the number of elements in it.
Oh, I have to think. B minus A is the number of elements in an inclusive range.
No, B minus A
Wait.
plus 1.
Plus 1.
So for example, suppose we have the numbers from 1 to 3.
When you say inclusive, you mean it just contains every number within that range?
Contains both ends, yeah.
Okay.
So if you have the numbers from 1 to 3, 3 minus 1 is 2, because 3 minus 1 is leaving out one of the ends.
Right. So you add 1.
Yes.
All right, so here's the fenwick tree with this padding for the min. And then now we go from right to left. We need to... Let me think. So maybe we don't update the value yet. Maybe we first get...
Yeah, well, we can...
Prefix, what's it? Prefix sum. And then the right would be nums I. And then...
Sum,
oh,
right?
Prefix sum. Right. And then the left side would be like...
Oh, no, so actually we just need the numbers less than it, so we don't even need a left side.
Oh, yeah, because it's going to be 0 because we're doing it from 0 anyways. Right. So it's just the prefix sum of that.
Exactly. The only thing we have to do is account for the fact that the numbers are shifted. So it's actually nums I minus mn minus 1.
Yeah, because it's padded.
Right, and the minus 1 is because you want strictly less than.
Not including that one. Right, that makes sense. So it's like minus the min.
Minus 1.
Minus 1. That makes sense, but I wouldn't have thought about that until I get like a wrong submission.
And then now you want to update your fenwick tree, and then fingers crossed.
All right, let's see. So first, let's put this in the answer. And then let's update. Is it update or set? And then we're going to set the value at nums.
Or you can use update even to just increase it by 1. I think that's probably the easiest way. Update, probably.
And then this is just going to be the old... How do you know what the old value is? Oh, this is an increment for update. Use the
update one. Yeah.
I see. Yeah, so set is not the right API to use there. So update at that index, and we're going to increment by 1. Fenwick tree.
Fingers crossed.
LeetCode says don't subtract 1. But we'll see, LeetCode. Let's see.
Let's see.
Uh-oh. All right. So maybe...
So now... So, okay.
Maybe it went like...
this is actually easy. So
maybe it's like...
Go to the Fenwick tree code. Up. We're going to go there in a second.
Okay.
And in the... okay, so you have that. So you have...
All right, I'm subtracting mn. Not ending. Wait, what did I do?
I said
I was supposed to... Wait. All right. Number says, don't worry about what he said.
Let me read through your code, and then I could probably see what's up.
So is it like going out of bounds because the size is only so much, and we're not actually ever going to reach the max, like what LeetCode is saying?
Oh, the update. The update you don't subtract 1. I thought you only subtracted 1 above. Yeah, absolutely.
Right.
You don't subtract 1 in the update. Sorry.
LeetCode should have won some big money if we had made a bet. Yeah.
There you go.
Yeah, Chat Sharp. They got that Eagle Vision. Great. There are multiple ICPC world finalists out there.
I should have seen that. That I should have seen. That's But you know, when you're this is a tribute to you actually. Like when you're doing it live and you're streaming and thinking about what you have to say, it's much harder to spot things. So
yeah, for sure.
Yeah. Yeah. So also, Fenwick tree answers are pretty fast. The code tends to be pretty quick, and we'll look at the implementation in a second. So yeah.
Okay.
Not bad.
Pretty cool.
Okay, so we did it. Okay, so now we're at the final part of the lesson. This is where we're going to end, and this is going to be how do Fenwick trees work? Okay. So, and part of the value of this is if you're not as comfortable with bit arithmetic, we're about to get better.
Okay.
Because fenwick trees are also called binary index trees, and they're all about doing some bit twiddling,
Bit twiddling. I like that.
messing with bits. Okay. So I'm going to break this final part of the lesson into two parts: the prerequisites of messing with bits, and then just looking at how fenwick trees work. And I'm going to have an image for that.
All
So
right.
to start off, I want you to solve. You probably already have. This is an easy problem. Number 191.
191. Let me see. It'd be great if I just knew all the numbers off the top of my head. Whole number of bits. I have not solved it.
Oh wow.
Well, all right. Actually, I read about this problem in Elements of the Programming interview. Let me see if I remember the trick that they told me.
Yeah. Let's see. So it's coding the number of ones set in the number.
Yeah. So there's like, man, how did it
And yes, and
go?
do not do what Icy Black Deep is suggesting and
Oh,
just
the
use the
pop
built-in
count.
function. Do not do that.
All right. So it's like, while the number is something, is it like? I don't know if.
Just don't forget the parentheses because there's precedence.
Oh, I have to increment answer. I
Oh,
learned.
you want to send it. This is a betting one, right?
Yeah, I want to. Well, we're not gonna bet, but I can't remember if this is the little trick. It's like one of the very first things I ever learned when I
And you could
studied
have also used
LeetCode.
and equals if you wanted there.
Oh yeah, yeah, and then this way is like faster than shifting the bits
We're going
by
to talk about
one
that too in a moment.
and
So
and
you
doing
did it.
this.
You got it. Okay. So now we are going to figure out what just happened.
All right.
Okay. Using comments, I want you to try letting n equal the number 20. So you can do this in your comments.
Okay.
So
So
you can do it like below if you want, or in the middle of the function. So let's say, and so in binary, that would be 10100.
all right. So let's make the binary things. Say 1010. No, no, no.
So it should be 1 to 16 and 1 to 4.
10100.
There you go.
Yeah.
Okay. So we've got 20. Okay. Now, let's below it put n minus 1. So that's n. So let's do the bitwise subtraction by hand here.
Okay. Yeah. So 19, basically. What is 19? That is 19.
Okay,
Wait.
but you did it because you
16.
knew what 19 was. Let's do it like we were in grade school, trying to do like carrying and subtracting.
Oh, man.
So if we subtract 1 from 0,
Wait,
that doesn't work. So we
let me do.
we
All right.
carry the 1.
So
make
1
it
from 0, so we gotta like borrow 1 from here,
Yeah.
and that turns into a 0,
Yes.
and then we bring it here, and then this,
Becomes a 10, and then we subtract 1 from that and becomes a 0.
and
Okay,
then
so it becomes a 1. 1 becomes a 1. 2 minus 1 is 1, right? And then
is that so? So then this is 0.
well, I wouldn't change those, but like I would just do it below, right? As in, like, put the result below your line.
Oh, wait. So let's not change these. Use my pen, Icy Black.
Yeah.
So, man, I can't do grade school math. That's what I've learned right now.
Well, let's write the result below. Maybe that'll help. So
All
the
right, so
result that you have.
this would be like 0. Wait, 1. Yeah, because we gotta borrow
Well,
1
it's
there.
not going to be 0. But so let's see. So you borrowed a
Wait.
1. So okay. So if you borrowed a 1 from 4, that becomes 0.
This is 0.
So the one you crossed out becomes 0.
Yeah, and then
Okay,
this
and then
becomes
the 2
1.
becomes 10. 10.
10.
Right, and 10 is 2.
Oh, because that's worth. 2.
Right. So then we subtract 1 from that, it becomes 1.
And then we send it here.
Yeah, and that becomes 2.
Oh, because it's 2 2s there.
So right. So now when you subtract,
I'll just
you
put,
get
yeah. I'll just write
it's
a
1
2.
0. 1 0 is 2. 10 is 2 in
Yeah,
binary.
yeah. So
And then you get right, and then you get 1 below it. Right.
right, this is confusing because I don't think I've actually done subtraction in binary like by hand.
And then the rest of the numbers just copy down. So you get 1 again in the next column, but you
And then
from the carry.
0, and then 0,
And then 0,
and then
right.
1. I see how that works.
And then 1.
Thank you for
But
the lesson.
we can but that was like painful, right? We can do it.
Yeah.
We can kind of learn from what we did. Okay.
All right.
Okay, so let's remove the pen stuff, and
Okay.
let's look at what it. Let's just write the answer below typed out.
See you numbers. Thanks for tuning in. Have a good night.
And thanks for helping.
Oh yeah, thanks for the eagle vision and everything. All right, sorry. So you're saying
So below the answer was, as you had it before, 19. 1 in the 16s and then 2 in the 1, right? Yeah. Okay. So when you subtract a 1, what it does is it turns all of the rightmost zeros into 1, finding the first 1, and sets that to 0, and then it stops.
it does. I see.
Okay. So it goes. It just. So,
Yeah.
And if you want to think of it differently, which might be easier than subtraction, if you added 1 to the number below, it becomes the number on top.
Yeah, because these would have to. Now that becomes 2. We can only fit 1 there. Yeah.
And that becomes 1. Right, exactly. So what this does is it turns all of the rightmost zeros to 1, and then finds the rightmost 1 and changes that to 0.
Right.
Okay. When you ampersand this with the original number, everything to the left of the rightmost 1 is left alone, because it's the same as it was before.
Everything to the right.
To the left of the rightmost 1 stays put because you never change those.
All right. Let's see there. 1 0 0 0 0.
Okay. Now what's happens below, right? Everything to the and then. So the effect is you zeroed out the rightmost 1.
Yeah, I see that. So basically, this turns into a 0 here.
Right. So it finds the rightmost 1 and it zeros it.
Yeah.
Perfect. So if we look at your bit count code above, what's great about what you implemented is instead of like running in 32 bits or something.
Yeah.
It runs only in the number of 1s.
Yeah. So it's like O of set bits instead of O of how many bits total.
Perfect. So the first fact we want to remember now about bits, we only have 2 facts, is when you do n and n minus 1, you zero the rightmost bit.
Okay.
Fact number 1. Last fact. Okay. So here's my problem number 2 for you in bitland.
All right.
What is the value of n ampersand negative n? So we can do that below in your comments. Use the same n. I want to do n ampersand negative n.
I don't even know how a negative number is in bits.
Right. So let me tell you how to make something negative. Firstly, before we do that, let's complement. So what happens when you ampersand something with its complement, meaning we flip all the bits?
Hold on. Let me type this in there to start fresh. And then he said, what happens when what?
Let's say first, let's do tilde n. When we complement all the bits, we turn zeros to ones, flip everything. Tilde n, right. So if we go below for tilde n, that'll just be taking the same thing and flipping them all.
I didn't even know tilde n is a thing.
It is, yeah. Okay, and if you ampersand those 2 things together, you get 0.
Yes.
Because
because nothing is the same.
Okay. The way you negate a number in 2's complement is you flip them all and then you add 1.
Wait, so this is called a two's complement, you said, this
That
little
that
squiggly
that's
line?
called the complement. The two's complement representation of numbers. To negate, you tilde and then you add one.
Alright, so this is the tilde,
And then you want to take that,
and
and
then
then I want to add
this,
one to it.
so adding one to this, it would be like that
And you can just
overflows,
do it by hand. Yeah.
and it becomes that.
Right. Okay. Now ampersand that with the original number.
Alright, let's see. So that gives us 0, 0, 1, 0, 0.
It gives you the rightmost one.
Oh. Alright.
Because if you think about it, when you tilded, when you complemented all the bits, that would zero out everything. But when you added one to that number, it set all those ones to zero and then only put a single one
In
where
the
the
right,
zero was.
yeah.
So you only get the rightmost one.
Learning
So these are
something
two
new.
bit tricks that we just learned.
Yeah,
And
I
there's a
didn't even
bunch.
know this existed.
There's like a people like these things because they're tricky things you can do with all these bit operations, and like they're sneaky and they're fast on a CPU because they're just using these
Yeah.
simple bit operations. So
Interesting.
we have two operations. We have n ampersand n minus one that zeros the rightmost one, and we have n ampersand bitwise and negative n, and that finds you the rightmost one.
Wait, you say negative n.
Yeah,
So
so
this
tilde
is
n plus one is how you get negatives. So technically speaking, there would have been a bunch of ones to the left. So if this was like a 32-bit integer, there was a bunch of zeros to the left, and all those became one.
and that's how it tells if it's a negative number.
The negatives are and we could talk more about this. We could do bits all day, but I think I just wanted
Right.
these two facts.
Okay, I'll
Like,
look it up one day maybe, but I think I kind of see where it's going with the when you say it's negative.
well, one way to see that this is the negative of the original number is what happens when you add n and tilde n together.
So these
You
two
can do that right above.
numbers.
You get all ones, right?
1, 1, 1, 1, 1. That is true.
And then what happens when you add one to that? They all clear out and give you zero.
Right.
So tilde n plus one is exactly the value you need to add to the original number to get zero. So that's why it's the negative of it.
I see. I think.
But anyways, so we have. So I agree. This takes time to get used to, but it does. But let's just remember the two facts because that's all I need. I need that n and n minus one clears out the rightmost one, and n and negative n finds the rightmost one and gives it to you only.
Yeah, got that.
Got it.
At least
Okay.
for sure I got this one. This one is like embedded in my brain. This one I'll have to add it. It's a new entry.
Well, so now I have a picture for you. Here you go. A link in Discord.
Ooh, picture.
This is going to be a crazy tree.
Oh man. All right.
Okay. So here's a tree you've never seen before.
Never seen it.
So I'm going to ask you some problems. So this is modeling an array. This is the kind of the structure of the fenwick tree. This is modeling an array that has 16 elements indexed from 0 through 15.
Okay.
Okay. So I'm going to ask you a few questions about this tree that you just have to look at it. So first question, what is true about all the numbers in the leaves?
There's only
If you read them from left to right, the leaves.
Wait.
Exactly. The leaves are all the odd numbers. Every odd number is a leaf, and those are the only leaves.
Okay.
Okay? That's the first fact. Second fact. what is true about all the numbers on the first level, and then what's true about all the numbers on the second level, and then what's true about all the numbers on the third level.
There are odds and evens and odds and evens.
So there's all sorts of mixed, but actually it has something to do with the problem you just solved.
What do you mean by that?
Well, think about the LeetCode problem we just did. And
The
what can
number
you
of
say about all the
bits?
binary representations in the first row, the second row, the third row?
Oh, so oh man. If a number has an even number of bits set, that means it's odd. But if wait, not,
so
well,
the number is
kinda.
odd if the last bit is set.
Yeah. Wait. So these all have 2 bits set.
Yes. And what about the next level?
Wait, but this one is like, hold on. I think I got confused about something. So these are the number of bits set is like, they're all the same number of bits set on each level.
Right. So the level 0 is 0, and level 1 has
Yeah.
1 bit set, and level 2 is 2 bit set, and level
Right.
3 is 3 bit set, and level 4 was 4 bit set.
Yeah, I got that.
Yes. Okay, great. That was question number 2. Question
Right.
number 3. Here comes a trickier one. How do you get from a node to its parent?
You just remove the rightmost bit, maybe?
Yeah, the operation we just learned.
Is that true? You just zero the rightmost bit and it becomes its parent.
So that's how this tree is designed. The tree is designed so that the way you get from a node to its parent is removing the rightmost bit.
That's kind of crazy.
Yeah. So one last question. How do you get from a node to its next sibling? Like, how do you get from, let's say, 5 to 6, or from 2 to
siblings.
4, or 9 to 10?
That's a good question. It seems like
So I'll give you a hint. You add something.
I was about to say, it seems like you like add 1.
But you add something, and it's relevant to what we just went over.
You add the right. No.
You had it.
You add the rightmost bit? No.
Yeah, so let's start at 9. What happens when you add the rightmost bit to 9?
It's 1, so it becomes 10.
And what happens when you add the rightmost bit to that? It adds the 2 to it, and it moves over again to the left, and you get 12.
Well, but I was looking at this 11. Oh, because they're not siblings. I was like,
Not siblings.
that's why I stopped.
Right.
I was like, hold up.
No. So you just answered my next question. If you don't have a next sibling, where do you move? To the next sibling of your parent. And if that doesn't have a next sibling, you move to the next sibling of its parent. Or you just keep going up, right? So you say, oh, 11 doesn't have a sibling. Does 10 have a sibling?
Yes.
So you move to 12. If you add 1 to 11, you go to 12. Right. So let's do another one. Suppose you're at 5.
All right, we're at 5.
So you go to next sibling, you get to 6. What happens when you do it on 6?
There is no next sibling.
So you go up to the parent. Does that have a next sibling?
It has a next sibling.
So 4, exactly, and it goes to 8. So
Wait.
So whenever you add the lowest bit, you either go to your next sibling, or if that doesn't exist, you go up and try going to its next sibling, and so forth.
I don't get that part. So you said
If you start at
the 6, right? Let's look at the 6.
Yeah.
And we add
the lowest one.
Oh, the lowest set bit, right? I forgot about that, even though we just went over it 2 minutes ago, and then it becomes 8.
Over a lot of stuff.
Yeah,
yes.
That makes sense.
So okay, so those are the 2 tricky things we need. Okay, so now let me tell you how the Fenwick tree works. Okay.
All right.
And it's depicted here. Each element will store the sum of all the indices from itself up to its parent, but not including its parent. So let me give you an example. If you look at the node 14,
14.
it stores the sum of all the values from 12 to 14, not including 12. Because 12 is its parent and it's 14. So it'll store the sum of the index 13 and index 14, A13 and A14.
Oh, like you're talking about metadata or something
So there's an array,
in
there's an
there.
underlying original array, like the array we're looking at the prefix sums of. So
Yeah.
the original array is called A, and node 14
Oh,
will store the sum of A14 and A13.
yeah.
Node 12, because its parent is 8, will store A9 plus A10 plus A11 plus A12.
I see.
And then 8 will store the sum of
Yeah.
1, 2, 3, 4,
Up to
5,
8.
6, 7, 8, and then 0 just has 0 in it.
Right.
Or yeah.
Yeah.
Okay. And 4 will have the sum from 1, 2, 3, 4. 2 will have 1, 2. 5 will just have the sum of 5 in it.
Right. I see
Okay.
that.
So whenever you want a prefix sum, you just sum your way up to the root.
Let me think about that, what you just said. Whenever you need a prefix sum, you just sum up to the roots. So this has 0 to 8, 8 to 12, and so you just go to like 14, and then you sum up all these sums together to get the prefix sum.
Right. So you just follow your way to the root to get any prefix sum.
I
So if you want
see.
this, right. So this is the sneaky way in which they're storing all the parts of the sums so that we can update them quickly. And the
Oh,
last thing is, how do you update an element of the tree?
okay.
And I'll just talk about this briefly, but let's say we wanted to increment 5 by 1.
Okay.
So we know that all the prefix sums bigger than 5 have to get fixed. Because the incrementing 5 by 1, index 5 by 1, affects the prefix sum from 6 and from 7 and from 8
Yeah.
and from 9, all right. So what you do is you increment 5, you increment the entry 5 in the tree, and then you go to the next sibling, and you increment that.
Right.
And by incrementing 6, that automatically increments 7, because when you compute the prefix sum from 7, it has to come up through 6.
Right.
And then you go to the next sibling, but that'll give you,
Nothing.
so that goes up and then goes
So
to the
we
next
go.
sibling.
So we go to like 4's sibling, which is 8.
And then you increment that, and that increments everything in the subtree,
And then we're done.
because now you're left the tree if you go any further.
Yeah.
So that's how the two operations of a Fenwick tree work in this crazy bit twiddling nonsense tree.
Wow. So what is that time complexity then? Is it just like, oh, the
Everything
height
is
of the
log
tree?
n.
Yeah, the height of
Everything
the
ends up being
tree
log n.
or
So
log
if you
n.
look now at the code, I bet you will understand what it's doing.
Let us see what the code says.
So let's look at prefix sum first.
All right. So if the index of the thing returns 0,
Mhm.
and then the tree index. What is this tree thing?
So index, so remember, the tree is stored as an array. So let's
So
suppose the first one you're plugging in there is, let's look back at the picture again. Pick one of the indexes.
let's see 6.
Okay, so let's say we want to do the prefix sum from 6. So we go to the 6th element of the array, and we get that value. And that gets added to red. Whatever's in the tree index 6.
Tree index 6 would be this red part, like this, or no? Am I
No,
tripping?
it's just, it does represent that red part, but it'll be some value, like, who knows what it'll be.
Right.
-4. I don't know.
Okay.
It's some number that's in that node.
Okay. Okay. So it's just some number,
Yeah.
and then
And then if we're at the root, we're done.
we're done. And then now this is
Otherwise, what does the
doing.
next line do?
Oh, this is that bit thing that unsets the rightmost bit,
Yeah, and that goes to the parent.
which is the parent. And then now it
Do it
adds the
again.
parent. Interesting. Okay, I see what you're saying. So this is doing what we talked about, where if we wanted to find like the sum at node 14, it's just you're following the path and you're adding up all the sums to that path, right?
Exactly. And through bit twiddling, you now know how the instruction you need to get to the parent, anding with n-1.
That is a little bit crazy.
Yes.
I kind of see how it works, but I can't say
Yeah,
I'm like
proving this,
very
we haven't proved anything, but you have a flavor for what it's doing,
yeah,
right?
for sure.
Okay, and then
Interesting.
last one, and this is the final thing, and then we're done. Update.
Update.
So just let's just understand what it's doing, right? It says increment the tree at that index. So I'm also maintaining the raw array underneath, so I'm saying you should increment that too.
Okay.
So
So
yeah, keep going. Sure.
yeah, so we increment this by however much the increments, and then now we're adding that amount
To that
to
node
that
of the
node
tree.
in the tree.
Yep.
And then we're
And then what does the
moving,
next
we're
line
doing this
do?
negative. Oh man, I just learned this. Hold on. This is the tilde thing that you're talking about.
Yeah.
And then you said, man, I already forgot. I
So
already forgot. Wait.
yeah.
You tilde them. Wait, let me go back to my notes. Oh yeah, you get the rightmost bit.
And then we added that. And so what does this operation do? 28?
You're adding the rightmost bit to the index, which means we just went over this also.
So if you look at the picture, what happens when you add the rightmost bit to a node?
Is it the sibling?
Exactly. You jump to
Yeah.
the next sibling. So what we're doing is keeping on walking to the next sibling over and over again and always incrementing.
All right, let me go back to that code. So yeah, you're walking over to the next sibling. But then what happens when you talk about going to the parent sibling?
This does it automatically, and we can see it in the picture.
All right, so 6 doesn't have any siblings. And you add the rightmost bit, and it goes to 8. That's right. We went over this. Wait, is that right?
Exactly right.
That is right. We just went over this. And then it goes to 8. And then how does it know it stops? Because
So you either pass the size of the tree,
oh, so
or
like
if you happen to have asked it to do 0, it just stops right after it increments it, because 0 has
right.
it will just stay
So
at 0 forever.
so when we go to 8 and we try and add the rightmost bit, we'll get 16, and it goes out of bounds, and then that's where this part will trigger and it will just break.
Exactly.
Very cool.
Exactly.
I get
So-
the gist of it, but
Summary.
yeah.
The summary for today. We first did the order statistics trees. Easy paste at the top of your file, and bam, you can solve problems you never solved before.
Yeah.
And the question it answers, and maybe I'll let you answer it. What's the question the order statistics tree answers?
How many numbers to the right are
Yeah, how
greater
many-
or smaller or something?
Yeah, like how many values in the set are less than?
Yeah,
a
how
given
many?
value?
Yeah.
Perfect. And then we solved some problems with it. Then I showed you about fenwick trees. Now, as we said, fenwick trees are a little bit of a novelty. It's like now you know about them. It's possible that you'll forget about them. It's possible, but the hope was A, you now know what they are,
Yeah.
and B, you also saw that there's some sneaky bit twiddling that people do, and you learned about that. And then also the fenwick trees can be used to solve some of these problems. But if on a later date me or someone else shows you segment trees, you might find that those supplant these. It's just longer code for the that segment tree.
All right. Yeah, I can't wait to learn about these segment trees then.
Yeah, and segment trees. So segment trees will also be even better in some respect because segment trees not only let you do sums of ranges, they would also let you do the max of a range or the min of a range.
Oh, interesting.
So they let you do other range queries.
Right.
But I think we've more than did enough for today. I hope that was interesting.
Oh, that was very interesting. I think now I at least have an idea of how these things work. So when people talk about fenwick trees, I'm no longer completely clueless.
Yeah, I think the most common thing is I'm not sure how much they come up in chat, but often when you're looking through the solutions of some of these problems, immediately someone will say implemented using fenwick tree, and then you'll be like, what the hell's a fenwick tree?
Yeah, basically.
The other aspect of fenwick trees that, and one of the reasons why people like using them in the solutions, is they're very fast. So the fenwick tree solutions will be faster than the order statistics tree solutions often for the same problem, or the segment tree, because all it does is a little bit of these bit operations.
Yeah.
So it's log n, but it's like a fast log n.
Right, but when we're talking about LeetCode, this doesn't really make a
Doesn't matter at all
difference.
for competition, but if someone's like trying to get like the 99% thing,
Yeah.
they'll use the
super
fenwick tree.
optimal stuff, right?
Yeah, because it sometimes will get you like higher on the percentage leaderboard.
Yeah. I get what you're saying.
But
Oh,
but yes,
man.
I think you might like look like in like yeah. Once you learn segment trees, you may never care about a fenwick tree again. But you heard about them once, and that was
Right.
my hope.
So thank you for showing me the fenwick trees before the segment trees in that case, because if I learned segment trees first, maybe I would never look at a fenwick tree ever.
Correct.
Yeah.
You probably wouldn't. And yeah, so yeah, but my hope was that in the process you also learned a little bit about the bit, and you also learned that interesting way of translating that other problem into a prefix sum.
Yeah, that was a neat technique. I'm sure that technique comes up at least in other problems.
Yeah.
Maybe.
And you also did a prefix sum problem today, and this is all about prefix.
Yeah, I think maybe this weekend is going to be prefix sums on the contest, but we'll see.
Yeah. All right. So I hope now there'll be a bunch of hard problems. I'm yes, it might be tricky to just all of a sudden start solving problems with fenwick trees, but I think those order statistics trees are within your grasp.
Yeah, for sure. Especially I've used like the sorted list in Python a few
Right.
times. I'm familiar
So
with,
you just gotta
yeah.
copy those 3 lines and bam.
Yeah, so that's great news for my rating, I hope.
Yes. I'm
Um,
hoping. I'd like to see it go up so people who are betting no just start losing their
yeah.
points.
Yeah, that'd be great. But man, whoever sat down and decided to build a fenwick tree, they must have been really bored. Because that's a lot of brain juice to go into this data structure.
Yeah. Yeah. Okay. Well, I hope that was enjoyable. Maybe sometime in the future, me or someone else, you have a lot of smart people in your chat. We'll go over segment trees with you, and good luck on your
Yeah,
coding.
maybe I'll start a rotation where everyone gets a chance. Because I know Lead Coach, Raxo, BetSim, there's so many people.
Yeah, you've got a lot of
Yeah.
great people.
All right, Brett. Thank you very much for that lesson. I'm sure everyone here appreciates that. And I think I learned a lot today.
Very welcome.
Yeah.
And yeah,
I think the
good luck.
most important thing is now I'm not so scared. Before I used to be terrified, but now I think you've given me the confidence to tackle these problems.
Yeah, there's actually a whole list. You think you could just look up, like by tag or something. There's a bunch of problems like this, and there you probably have all these problems that you can't solve, and then all of a sudden they're just like all like, oh,
Yeah,
that,
I might
that
try
worked.
some. Maybe we'll try one right now, but we'll see. That was a
Yeah,
lot of
I'm
brain
not sure if I
juice.
looked at the lead coach one that he put in chat, but that might be one of them. Yeah, and then yeah,
Yeah, cool.
okay,
All right, Brett, thank you very much once again, and
very welcome.
Take care. See you around.
See you around.
Thank you very much. Oh man, what a lesson. Let me get these headphones off. Did I do that right? All right. Yeah, I don't like to wear those headphones. But everybody, that was Brett. Brett right here in chat. Brett has been basically tutoring me for many years on stream. I don't know how many of you know, but Brett actually gave me some private lessons right before my Google interview that came in really handy. We got on a Discord and he gave me a lesson on like just the regular data structures, like how to implement all the data structures. And on my interview, one of my interviewers was asking me in great detail about like how are hash maps created under the hood, or how are sets, ordered sets, unordered sets created. And I don't think I would have answered that if it wasn't for Brett's lesson. So thank you very much, Brett. I think you're a big reason why I am where I am today. You and so many other people. Oh yeah. Control Alt Scalderon, how are you doing? How about me? How about me? I just got a lesson. So let me see lead coach's problem. Man, should we do this right now? I feel spent, but I got this. Oh, it's on a blind 75. Find median from data stream. Let's read it and let's see if we can think. The median is the middle value in an ordered integer list. If the size of the list is even, there is no middle value, and the median is the mean of the two middle values. For example, array 2, 3, 4, the median is 3. For example, array 2, 3, the median is 2 plus 3 divided by 2. Implement the median finder class, where the constructor constructs the thing, has a method add num, takes in a number, it adds the integer num from the data stream to the data structure, and find median returns the median of all elements so far. Wait, I don't even, where's that? I should have bookmarked those 3 lines of code, but I think I have it in BetSimps thing that I bookmarked. It's the same thing. I'll just take this one. Too many tabs. I've done this one and it's not that bad if you know the data structures. Yeah, I think I've done this also with like a double priority queue, but maybe we can solve this with one of our new data structures. I'm thinking what was this called? What did Brett call this? I forget. Man, let me just, was it 315? Ordered statistics tree. Yeah, let me pull up the template. Ordered multiset is what you called it here, which doesn't really make a difference, but I was just curious. Ordered set, ordered multiset. I guess multiset might be more accurate. Wait, BetSims is not a multiset. Uh-oh. Interesting. Is it? Oh, less type and less equal. Oh man, that good thing you pointed that out, Brett, because I probably would have tried to use the wrong thing and then made some big mistakes. So all right, I'll use the multi-set one for this. I gotta save. Let me bookmark this solution here. All right, median in a stream. So I suppose with this, I just keep adding numbers to the multi-set and then find the size. So if the size is odd, we'll just take the middle, the index at the middle. And if the size is even, we'll take the two middles and divide them by 2. Can we do that? I don't even really know the syntax here, but let me try it. So this would be, hopefully, this is odd size. Destroyer Jot, thank you very much for the follow. So in an odd size, we'll just take the middle as size divided by 2. But how do I get the index at a certain, is there a way to look up an API for this? Find by order. Oh, and that returns an iterator. So it's like find by order. Where can I read about the API? Is it just the order statistics node update tree thing? Brett is the API reference. All right. That's cool. So in that case, it would be just that. And then if it's even, then, so if this was 4, then 4 divided by 2 is 2. And then we want -1 of that. So or what did maybe I'll call this like right mid. And then maybe this should be a double. So that's right mid. Then it would be like right mid -1. And then divided by 2. Right? Hopefully this works because I've never solved this problem using I don't even know what to call this. Ordered multiset, I guess. Uh-oh. That's because I didn't even make it, man. I didn't even make the dang thing. That's what's happening. Jesus. Did that? Gee, man, everything is so easy now. Um, thank you very much, Brett, for teaching me this. I think I'm gonna do so many problems. I might even get some Q4s now on the contest. I think I've only solved Q4 like 2 times in my whole life, but maybe it's gonna be a lot more now that I know these things. This is a different approach from what I did. Yeah, I think, let me see my previous submissions for this problem. I'm sure, ooh, I've never solved it before, but I've solved this. I think Eric Toe taught me how to solve this with 2 heaps, I think. Um, is this considered cheating on an interview? Um, I don't know. Is it? Maybe they'll ask you to solve it without using an ordered multiset. Um, no more Python. Yeah, I don't need Python anymore. Actually, for Python, I still use Python for like string problems sometimes. All right, 493. You might get cool points for knowing the data structure. Yeah, it might be a way to flex your advanced algorithms knowledge. Especially if you can solve it with the 2 heaps way, and then you just hit them with this and be like, man, which one do you want? I got them both. "493. Reverse pairs. Hard problem." Youssef 1G, thank you very much for the follow. Reverse pairs. Given an integer array nums, return the number of reverse pairs in the array. A reverse pair is a pair ij where I and j are in bounds and nums I is greater than 2 times nums j. All right, this one isn't immediately obvious to me, so I'll probably have to actually think a little bit. At least go through my regular motions. Hope you had a great day. Yeah, today was a great day, I'd say. Let me see what happened today. Big things happened today. One, I learned a bunch of new things in some advanced LeetCode. Brett taught us a bunch of crazy stuff. 2, I did some good work at work today. I got some, like, this really cool dashboard that I've been working on for the last week. And 3, I got a spot bonus today. That was nice because we've been working on DMA, and now DMA is launched, so we got some money. So I'm very happy. So yeah, my day has been really great. Mohammed Hamdi 98, how are you doing? You can use a max heap on the lower half and a min heap on the upper half, and to keep the median. Yeah, that's the 2 heaps technique. I broke my head doing merge sort for this. Merge sorts. Ending with Ali. Thank you very much for the raid. What's happening? How are you doing? Are you LeetCoding these days? Real Raymond Jones, what's up? Dashboard? I thought you did C++. Yeah, I do so many things at work, but I did build a dashboard. It wasn't, yeah, it was UI and data and everything. Now I'm unemployed. That's even more reason why you should be LeetCoding. I was doing a quiet co-working stream. Nice. I find co-working streams are very, very, very productive, especially if you have troubles like me focusing when you're by yourself. Oh wait, oh dang, I can't read. My B, you can't read, man. So you're employed. You don't need to be doing LeetCode, man. LeetCode is so fun though. But thank you very much for the raid. Hopefully your co-working stream was productive. These reverse pairs are almost inversions. Wait, LeetCoach. What did LeetCoach say? are called inversions. It's an important concept in programming. Inversions. Never even heard of that. All right, so what we're doing, we're trying to figure out how to solve this problem. So nums I is greater than 2 times nums j. How do we solve this? I'm guessing it has to be with that sorted, ordered set thing. But let me try and figure out how we can do it. I guess this is kind of like asking for, so if we go from right to left, yeah, I think I got this. We go from right to left. We're inserting maybe 2 times the number into the tree. And then when we get to I, we're going to do a query like how many numbers are less, yeah, how many yeah, it's the same thing. How many numbers are less than this to the right? I got this. The reason I ask you this one is, how do you count numbers greater than x using this? Oh, try going left to right. Oh, did I mess it up? Brazen Intellect, thank you very much for the follow. And SA9, thank you. Yeah, so I'm thinking, all right, let me copy and paste that thing first. Man, I need it like on speed dial. Where is it at, man? I just bookmarked the thing. Let me rename this to TAC Vector. Thank you very much for the follow. What is this called? This is called ordered multiset. And then we're just going to use these 4 lines. All right, so my idea is to, let's create this ordered multiset of ints. Let's iterate from right to left. Oops. And then we're gonna first we're gonna find like how many it's, oh man, I forgot the API already. Order of key. Oops, order of key. And we're gonna look at the current number. And then we need to find how many pairs. So I guess that's just like we add how many. You might also want to bookmark the API reference. How do I do that, man? I gotta have Brett on speed dial. Careful, the numbers are big. Oh, snap. I see what you're saying. Thank you. Thank you for letting me know. But I think out of submitted, I'd have gotten the wrong answer and then I'd have adjusted. But you just saved me some time. And then now, I suppose a way to not do this with longs would be to divide by 2, but then that gets weird with odd even numbers, so I'll just leave the longs in. What are we doing now? Oh, we gotta insert. We gotta insert nums I times 2. Would that work? I gotta think. Oh, we gotta cast to a long. Right. Thank you, Brett. Is that what we want? This is my thought, but should I just run it? See? Man, I can't believe these hards are so easy now. Jesus. This doesn't feel right, man. For 4 years, I've avoided doing these problems. 4 years, man. I've shied away from all hard problems. I see a hard, I'm like, nah, I'm out of here. I see fenwick tree, segment tree words, and I'm like, nah, forget this, man. I'm gonna go play Stardew Valley or something else. And now, yeah, 4 lines of black magic, and then all these hard problems literally become easy mediums at most, you know? This is insane. Big gains, real Raymond Jones. You're absolutely right. I chase coins. What's happening? Geeks for geeks. Should I be using geeks for geeks? I'll just bookmark it just in case. Scroll down, it has examples. Oh. Alright, so we got insert, we got find by order, we got order by order of key, we got good old find. Yeah, that's all I need to know. Very nice, very nice. Blacksy Music, thank you very much for the follow. I don't know what to do with myself now. I feel like I have all this newfound knowledge. It feels a little bit cheap to me. These problems are actually hard, you know, and then they're just so trivial now. We solve too many problems, none left. With great power comes great responsibility, man. Oh, let me talk about my goals, man. I'm almost back in the 2000s. I can't wait to be back in the 2000s. That's like my goal this weekend, is to break 2K again. I'm like 1982. So this weekend I'm also gonna try and do the double header. I'm gonna try and do the bi-weekly, because now it's at 10:30 a.m. instead of 9:30, which I think I can wake up by 10:30. And then there's a 10:30 p.m. So with these 2 contests, I'm hoping I can break 2K. That would be great. Amazing door. What's happening? How do you do LeetCode without getting nervous? Man, do you mean doing LeetCode live on stream without getting nervous? Because that wasn't always the case. I remember when I first started, like, it was easy to do it when I first began because nobody was watching. I think I streamed to like 1 or 2 viewers max for almost 2 months before people started to show up. I don't think there was a very good LeetCode community on Twitch back then. Like, nobody was really doing algorithms except maybe Larry NY and AWice, and they'd do it like once a week, if that. So there wasn't already people like hungry for LeetCode on Twitch. So when I started streaming in 2001, it wasn't a big deal. No one was looking. But whenever I got raided, I remember one time Eric Toe raided me with like over 100 people. And I started to sweat everything. My whole skin is tingly. I'm like trying to solve a problem, and then all these people just came in and they're watching me. And I was getting super flustered. I couldn't even focus on the problem. And that was like, that happened to me a few times in the beginning of my career, of my streaming career. So I did get very, very nervous. Like maybe my voice even starts crackling and stuff. I'm like shaking. Oh man, so many people watching me make a fool of myself. And then now, like, now I can get rated by people with hundreds of viewers and stuff. And I won't get too nervous. Maybe I'll get a little bit, but nothing close to that one time. Some people don't know about, man, some people don't know about, we're talking about this chalk. I used to have a blackboard. I keep this chalk right next to me wherever I go. Anyways, Q Ultimus, thank you very much for that gifted sub to Brett. Very well deserved. Brett just taught us a very crazy lesson. Let me add another star up here. Q is the first name. So how do I not get nervous? I guess a lot of hours streaming, and then nervousness kind of dies off over time. But for sure, if you're thinking about streaming Amazing Door, if you're thinking about streaming LeetCode, I think it's well worth it for a few reasons. One, you get to interact with this community, which is a great community. It's taught me so much. Two, people call you out on your mistakes, and like you get immediate feedback, something that you don't get when you're just coding by yourself. Three, it makes it way more fun, and it keeps you more accountable than not doing it. Four, you can practice talking out your thought process as you're going through the problem. So instead of doing a rubber duck or whatever, or coding in silence, which is not realistic for interviews, you're forced to like talk as you're solving the problem, which is a big deal that people don't practice during interviews, like interview training. So I'd say go for it if that's what you want to do. And I'm very happy to see that a lot of people in chat are streaming now. The real Raymond Jones streams every single day. He's been streaming every single day for more than 50 days. And sometimes he does it twice a day. But he can only stream for like 2 hours at once because his laptop sucks and it overheats. I'm Motive, man. You should do it. It's strictly greater than not doing it online. I think like you get so much positives from streaming. I had a question about your lighting. What fill and key light do you use for your setup? Man, I don't even know what those words mean, Q. But I got a light right here. I got a light right here. I got a light right here. Let me take a picture. Maybe I'll take a picture and post it in my Discord for you, Q. How about that? I'll do it right now. Uh-oh, my phone just died, man. Never mind. Wait. I need a new phone, man. My phone is like on its way out. Look, I even have band-aids on it. It's really broken. All right, here we go. Nah, I think my phone is... Anyways. Man, my phone is kind of like real Raymond Jones's laptop, man. It sucks. Big time. Kind of like my headset and laptop, yeah. All right, maybe I'll take a picture with my other phone. My work phone. Here we go, here we go. Smile for the camera, everyone. Yeah, I'll send it later. I have to like text this to myself and stuff. All right, let's see. Let's see. Man, why does my phone, it works usually, but today it's like super dead. Anyways, I'll send it later. Get a phone from the competition, an iPhone. I've been thinking, should I switch to iPhone? But then I don't feel like to relearn how to use a phone. And I think like all my photos and things like that. Can you use like Google on iPhone? Like Google Photos? Or do you have to use all that iPhone stuff? Yeah, you can use all that stuff. Man, my phone is like frozen right now. It's like it's not even doing anything. It's crazy. Maybe I'll go to the Apple Store tomorrow with my new spot bonus, man. I got mad bonuses coming in. I got this bonus, I got that bonus. I got my annual bonus coming in like a week or two. Maybe it's time to spend that money. Buy a new dang phone. What's a spot bonus? A spot bonus is like when some super high director gives people money. I got a pair bonus today too. A pair bonus is like when one of your coworkers gives you money. So I got, yeah, wilds, all types of bonuses. Look, now my phone restarted. Anyways, I saw the Google YouTube meme about pair bonus. There's a meme about them. Yeah, I work at Google. Obes. Pair bonuses are nice. I really enjoy. So we get 5 pair bonuses that we can give out to each other every quarter. There are some rules like you can't give somebody who gave you a pair bonus in the last 6 months, or like you can't give your manager a pair bonus or something like that. So there are some limitations on it, but we all get 5 pair bonuses to give to someone every quarter. And I try to make it a point to give all of mine out, all 5 of them. You're on the bonus grind? Yeah, I try and give mine out, man. I don't like to hold on to them. So anytime somebody works with me and they did anything basically, and it was an enjoyable experience, I just give them a pair bonus. I've had a bounty bonus recently at work. Had a deadline to get it. A bounty bonus. I've never heard. Maybe it's like the same thing as a spot bonus. Hold on, I'm still trying to. My phone just restarted. I'm trying to like send this picture so y'all can see what my lighting setup looks like. But I just recently changed my lighting stuff. You'll see it. I bought like a new light. It's in the middle. It's like a horizontal light. 1 second, man. Here it comes. I have to have it plugged in for my phone to work. Man, I hope I don't have anything to dox myself in this picture. But I'm about to send it anyways. Are y'all ready? Here we go. I'll pull it up on stream. Where's the Discord at? Well, let me let me look at my picture first. Do I have any API keys up there or something? Hopefully not, man. This is what my setup looks like. So I'm under some stairs, man. Like I have my desk under these stairs. I got this one light to the left. I got this tube light horizontally in the middle, and I got this other, I think this one is like a Elgato light to the right. 4-point lighting. Yeah, I got one behind me too. I used to have one above me, but man, it's just too much lights. Steven Sagiball, what's happening? Is your office in a closet under the stairs? Brent Arato, what's happening? It's not in a closet, but it is under the stairs. My apartment is in the basement. And so I have this basement apartment, and you know, under the stairs it's kind of like dead space. I didn't know what to do with it. So I just put my desk there, and it makes pretty good use of that space. Yeah, and I got there's more things. I got like lights behind. There's so many lights. Harry Potter style. I don't even know what that means, man. Calc 2 is too hard. Steven Sagiball. I don't think so, man. I think you can do it. Wait, how long have you been in Calc 2? I swear you've been talking about Calc 2 for a long time. Should we do some more problems, or should we just kind of chill? Calc 2 is the hardest calc, probably. Man. That's what people used to tell me, Brad. When I was in college, people were like, "Oh man, Calc 2, the hardest class on campus." But maybe I had a good teacher or something, or maybe I was focused during that class. But I thought Calc 3 was way harder. But maybe it was because I skipped class more in Calc 3 because it was boring. Like the professor was boring. Calc 2, my professor was like younger and more into it, you know. I thought Calc 1 was harder, more to cover in a semester. My Calc 1 professor was amazing, and it's like one of the only classes I got an A on. Flip a coin, heads chill, tails one more problem. Oh man, that is actually a good idea. I'll think about that. And UF Calc 2 was considered the hardest. I enjoyed Calc 3 more than 2. Interesting. I think it was because they all took Calc 1 in high school, so they were never used to college Calc 2. Good professor means a lot. Yeah, I had an excellent professor in Calc 1, and I never enjoyed a math class so much before. But I actually failed. I failed one class in college, and it was a math class. I'm sorry, Brett. And it was, what class was it? GG from YouTube. What's happening? Devin, are you talking about that AI chat or AI bot thing? Anyways, I'm trying to remember what class I failed. I think it was like something differential equations or engineering math 2 or something like that. I failed that so bad, man. Have you tried the other LeetCode problems like JavaScript and SQL? I just learned how to do SQL like in the last month, but I've never tried any LeetCode SQLs, and I've done a couple in JavaScript, but JavaScript isn't my main language. I prefer C++. My class is an online, and it's only like 2 months long. It's accelerated. Interesting. I got a D in discrete math and I had to retake it. I got 2 D's and 1 F, all in the same semester. That was a terrible semester for me in college. So I got 2 D's and an F, and then I think it was over the summer school, And then the fall, I just didn't sign up for any classes, and I just took like a semester off, and I went backpacking in Europe and stuff. And then I came back, and I was able to finish off my degree in a couple of years. Man, it keeps scrolling down. Is AI ever not a bot? LeetCode sequels are good for practice. Yeah, I've never actually done a LeetCode sequel. Starting off with optimization problems, which I hated. I don't even remember Calc 2. Oh, whenever you can use a fenwick tree, you can also use a segment tree, right? Right, nice. By JavaScript problems, I mean the few dozen that can only be written in JavaScript. I didn't even know that, Super Vaca Monk. I didn't know that there are only JavaScript problems here. I'm now kind of curious. Should we try one? Sleep, man. JavaScript. I didn't. Are these all new? Yeah, look at these numbers. They're all 2000s plus. Snail traversal. And you can only do it in JavaScript or TypeScript. That's crazy. I'm not about to try that. That's for sure. Yeah, thanks for sharing that. I had no idea. Have you looked into code forces? Yeah, I looked objects. I know what that means, man. I've looked at code forces. I've never done a competition there because I find the competitions on code forces happen at weird times for me. They're always like Thursday at 11 a.m. right in the middle of my workday. But I suppose I could do virtual contests, but there's no fun in virtuals. Shin Sean, thank you very much for the follow. All right, what are y'all saying? I suppose maybe my brain has absorbed too much today and it needs a little break. I gotta think about, was Ericto your tutor? Yeah, I can talk about that kind of stuff, I guess, just chill. Doing easy with a timer, man. Brett's pressing me. Ericto tutored me for maybe like 2 months or something. I remember I never even really knew who Ericto was until he rated me, maybe on my 12th day of streaming or something crazy. Like, I was really new to streaming. Ericto rated me, and then I checked out his channel, and apparently this guy is a dang legendary grandmaster in code forces. He has over 300,000 subs on YouTube. He's super serious. He knows all his algos really well. He's like world renowned, you know. This guy raids me, and then I think on his website he's said something like, I do classes or something. So I reached out to him on Discord and said, hey man, let me sign up for your classes. And he took me in. We met like every Wednesday or something, once a week, and it was a small cohort of maybe 3 or 4 other people in the class. And man, he went really in depth. I think Ericto is a big reason why I also passed my interviews. Right before my interviews, he went over like backtracking, and I was always weak at backtracking, and I could never do backtracking no matter how many times I tried. But Ericto walked me through, I think it was like N Queens or something similar, and everything just made sense. And I got a very, very similar problem to that in my interview. It was a hard backtracking, and I was able to code it like almost perfectly, I think. And my interviewer was like, all right, I've seen enough, because it was like a follow-up. It was like the third question in the interview. So he gave me an easy question. He gave me another question, and then he was like, "All right, Mister Algo guy, think you're hot shit. How about this hard question?" And he's like, "I don't expect you to finish it, but let me see what you got." I was like, "Oh man, for real, let me do this." And I was coding it up, and I was like, just flowing. I was just flowing out, talking just like I'm streaming. And then he just stops me. He's like, "All right, man, I don't need to see no more. Everything looks good. I'm sure you can do that." And then we just talked for like 5-10 minutes. And he asked me if I had questions for him and stuff. So I'd say I would not have been able to do that without Eric Toe. Mr. Take it or leave it. Yeah. Take it or leave it. I also never knew how to do that until... I don't remember where I learned that. I learned it on stream. I have all the VODs, but I learned that from... I think I tried... House Robbers was the problem that made that one click for me, maybe. Have you ever tried to solve the 1 billion row challenge? Marcosaurus's. How are you doing? I have never even heard of that. That sounds like the hot chip challenge or something. I don't know. What problem? I don't remember what the problem was, but it was a backtracking problem with... It was very similar to N Queens, but it was about like making a word with some lessers or something like that. I had something similar, a hard backtracking problem, but then we compiled it and it ran perfectly on first try. Wow. That's crazy, man. You had to compile it. That is even crazier. I remember the first time I watched the stream, we talked about avoiding infinite loops in binary search. I also remember that, Brett. I remember that very, very vividly. I was trying to implement a binary search, but I never knew how to implement binary search cleanly, and I was struggling with off by ones. And I never knew, like, this is actually one of the first videos I want to make on YouTube is about binary search. And I never knew when to use like greater than. Let me just pull up this thing real quick. Don't worry about this. So in my binary search, I always struggled with like, do I go like this or like this, or is it like m+1 m, or is it like... I never, like, none of this made sense. I didn't know how to do any of this, when to use which one. I didn't know if it's the thing goes there, less than equal to m+1 +1 there, or both of them +1. And Brett taught me. Like, ever since Brett taught me binary search, everything just made sense, man. And I remember what you said, Brett. You're like, everything works until we're down to the last two cases when we have some array of numbers. And then, you know, you have your left, you have your right, and then everything works until you get to like the last... I mean, I guess this should be like sorted, right? When you're down to like these two right here, this is where the money happens. And then Brett taught me some weird trick to like, whenever L and R are like only one apart, then we just choose the best value of the L's and R's or something. But anyways, DP Lopez Dobb from YouTube, thank you. What's happening? I don't think I really explained anything about binary search here, but yeah, I remember that, Brett, very much. So my style of binary search, I use this one because I think it's just so easy to remember. And in this one, I don't have to remember like which one to add the one to, which one to do this. It's always this. L equal this, r equal that, and then you just save the best one you've seen. So if it would be like, you know, if the midpoint is a good one, then you just remember that part. And I stick to this style. Every time I do a binary search, I do this style, and I think all you have to do is pick one and stick with it. Oh yeah, r equal, yeah, thanks. Keyboard sounds great, thank you. The key to binary search is to know your invariants. I don't even know what that means, man. The 1 billion row challenge is a fun exploration of how far modern code can be pushed for aggregating 1 billion rows from a text file. Has a repo in the GitHub. It's a good exercise. Interesting. I might check that out one of these days if I remember. The less than equal is nice. Yeah, less than equal is the way to go for me. But I see like a lot of the top competitive programmers seem to use this way. But it's so confusing, man. I never know which one to use here and which one to return. And it always leads to off by ones. And it just gives me lots of frustration. This way is the best way, man. In my opinion. Imagine what life would have been like without LeetCode for the last couple of years. Man, I think if I never started to stream LeetCode, I would have never been working at Google. I would have never been a Guardian, or not Guardian, definitely not Guardian. But I've never been a Knight. I don't think I'd have kept on studying as hard as I did. Demond, thank you very much for the subscription, man. Are you up here? I mean, let me just put you up here then. Thank you very much. Yeah, so streaming really, streaming really helps me out, man. Man, I just pressed some buttons. Let me restart that. Copy, paste. Oops. Hope I spelled that right. Oh, you're the new one on the next column, man. Thank you so much. Algorithms are fun. Yeah, now they're fun. I think I used to really struggle with the fun part when I was learning, but now that I've learned them, they are super fun. Means something does not vary. Here, Larry say invariant all the time. Man, still don't know what it means. Silent be overtaking LeetCode. Oh man, LeetCode's too far away. Don't forget all the people that got jobs because nah. Yeah, don't forget those people, man. Every time somebody gets a job and they post here that they've gotten a job, it makes me so happy. And it also makes me so happy to see so many people stream. I think I talked about this the other day. But when I first started streaming, there was nobody doing LeetCode streams, or almost no one. And now it's like every day when I turn on Twitch, there are multiple people streaming LeetCode every single day. And it makes me so happy. And I'm always lurking in those streams. Did you learn on LeetCode, or did you learn before LeetCode, then do the challenges for extra learning? I feel kind of strong in my Java development, but I'm learning Python and I feel like I am slow. I also know no algorithms, I feel like. I learned on LeetCode, man. When I first started to LeetCode, I never knew what a binary tree was. I never knew what a linked list was. I didn't know any algorithms. But I learned as I went on. I made some mistakes along the way. I tried to like just power through things without studying specific algorithms. I tried to like just look at the problems and think about them and solve them on my own. But after a while, I realized I'm missing a lot of knowledge. Like, it doesn't really matter how smart you are, man, because you need the knowledge also. You can't just be smart. You can't just think, oh man, I can just figure out these problems if I try hard enough. But a lot of these problems, it took like really smart people many years of their life to come up with these algorithms. Like, you're not gonna sit down and look at a medium problem that's asking to implement Dijkstra's. You're not gonna sit down and come up with that off the top of your head unless you're literally Dijkstra, you know? So I had to like think about that. I'm like, man, I'm just gonna learn what these fools learned before me and then do it that way. Man, this thing scrolling is annoying. Oh, what's the decision? Oh, also, hi, what's happened? Fire Codeman 69, thank you very much for the follow. And Ace Attack, thank you very much for the follow. When I took algorithms in college, it was so hard until I learned to LeetCode. Yeah, LeetCode allows you to practice, which I think makes the theory make a lot more sense. Are you a Fenwick fan or an order statistics tree fan? BetSimp, I gotta say, I'm a fan of both. Mainly because I think the ordered statistic tree is a lot easier to use and understand what's happening. But I'm like in awe of how the Fenwick tree works. And I can't believe somebody actually sat there and thought about a Fenwick tree. Is it named after the dude who invented it? Did Fenwick invent the Fenwick tree, or is it so, like, who is this guy, man? You know, look, this guy invented it in 1989. That's crazy. 1992. This is the most recent data structure that I use, that I know, probably. Imagine that. Like 30 years ago, this dude just came up with this thing. What a nerd. Yeah. Um I am machine. I never sleep. Welcome. I had to fix a binary search in my last interview. It was easy because I just moved a line, but I did understand all the code. Very nice, man. Yeah, binary search I think is a simple concept to understand, but once you try to implement it and you haven't had any practice implementing it, it's tough until you learn how to do it properly. Rafa J. Flowin in the house. What's happening, Rafa J. Flowin? Hope everything is going well for you, man. I created the Twitch LeetCode genre. I never created it, man. There was a lot of people before me, but I think I had strong impact on the genre. I always talk about Larry NY being one of my biggest inspirations to stream. Also, A Weiss, huge fan of A Weiss and Larry NY, and they came before me in the Twitch LeetCode genre. Knowledge is the most important as demonstrated by Ty Lopez. What? Um, yeah, you're not expected to invent calculus by yourself. Why do it for LeetCode? Yeah, some people, I think a lot of people, when they first start LeetCode, they try to invent the calculus by themselves until they realize, like, nah, you gotta study the patterns. Oh, type racer. We'll do a type racer in a bit. Let me catch up. Dijkstra brags that he came up with his famous algorithms in 5 minutes. Man, I was reading about Dijkstra, man. I read that everybody thinks he's a massive douche. Like, it's a unanimous decision that Dijkstra was a big douche, and his, what's the word? His ego is like so big. But I was actually reading, he has, I don't know if y'all know, but Dijkstra has really nice handwriting, and he has a bunch of notes out there somewhere. And one day, my girlfriend and I were kind of bored, and we just read all these notes by Dijkstra's, and and he even writes like a douche, man. Anyways, man, should I just make this larger so it doesn't go down? Fenwick tree is definitely omega wrinkly. Millennial discovered something. Yeah. Yeah, I know what you mean. Imagine inventing it and then it's named after some other dude that popularized it. Yeah, dang, is this guy still around? Oh, he's still out there, man. Dang, is this the guy? He's a professor. I wonder how he feels. Maybe I should ask him. Fenwick just described it 5 years later. Dang. Yeah, Fenwick. Strong impact. Alright. Is my girlfriend a sweet? No, she's not. But she's here for every stream and she watches. And I think she's getting FOMO from LeetCode after so many years of watching me doing LeetCode on stream. Alright, name that template. I can't even pronounce his name. Let's do type racer. Who's here for the type racer? We're gonna do this type racer. Maybe I'll chill for a couple more minutes. And it's time for me to get out of here. Solving C++. What's happened? Reedy from YouTube. I don't know what you're talking about. Bet simp. I see what you're saying. All right. My keyboard types backwards on Twitch. Oh, you gotta. Hey, how did somebody get in here, man? Is it the same racetrack? That's crazy. Someone's hacking me. Oops. Let me send that link, right? All right, the first race is the warm-up. Second race is the championship round. Warm-up time. Here we go. Yeah, I think it's the same URL as the last one. All right, let me see. Oh, no condom Chris, 94. Guests, we can't have guests winning 1 and 2. That's crazy. All you guests, if you're not actually guests, you need to log in. Raymond Jones, 69. Man, isn't it past your bedtime, Raymond Jones? What you doing up so late, man? It's crazy. All right, championship round. Here we go. That was a bad run for me. Dang. 2 guests, number 1 and number 2. I think that has literally never happened before, man. I don't know what's happening today, but look at that. 91 strike on bro, 98 six pack sexy aka no condom Chris, 96 93. Wow, these are the slowest times I've ever seen. Those two guests are in step together. Yeah, these are, I mean, that was crazy talk, man. That was a tough prompt. Yeah, that was pretty tough. So I don't even know what to put on the website because two guests won. Should we put unknown or man, I even forgot how fast it was. 112, I think. Oh, look, everybody's racing again. 150, Jesus. Kim Sylvia from YouTube, what's happening? Welcome, welcome. Yeah, these people are fast, man. These people are fast. Dang. Q with the 117. Alright, enough type racing. Let me put up, I don't usually put guests on the board, but I guess I'll do one today since it was like 1, 2. I'll just put guest. Alright, alright. What are y'all saying now, man? We are done learning fenwick trees and ordered statistics trees or whatever it's called. I don't even remember the name of that sorted list. C++ sorted list. But I got them bookmarked. I got the ordered multiset right here. And I got, well, it's right here. Ordered multiset. Robo Dom in the house. What's happening, Robo Dom? Thank you very much for that hydrate. Cheers. Should I have a penalty for a guess, like 10 WPMs? Nah, come on now. You never answered my question. What was the question, man? Did I miss it? I'm sorry. Wow, which screen you play Helldivers 2 on? I played on this one, my left screen. My left screen is like 2K 165 hertz, and then my right screen is like a 4K 60 hertz. So my left screen is my Helldivers screen, man. Oh, I'm playing Helldivers, man. Is it good? It's very good. It's very enjoyable. Lots of intense moments in that game. It's very frustrating at times, but in a good way. There is a lot of bugs and bad guys to kill, friendlies also to kill. There's a lot of friendly fire. There's a lot of funny moments, like if a drop pod just drops on you. Like, yeah, I'm having a great time with that game. All right, look at the time. It's time to go. It's midnight. So we'll raid somebody. But let me just say, if Brett's still around, Brett gave us a great lesson today. I think he unlocked me to the next level. Brett taught me about fenwick trees, taught me about that other type of tree, the ordered statistics tree or something. Yeah, I really enjoyed that lesson. I think it was well planned, and I think you did a really great job. I can tell you do this professionally. And yeah, if y'all didn't know, Brett is like actually a professor, a real life professor, you know. We just got a free college education by Brett. Thank you so much. All right, so LeetCode streamers, spooky. I guess so. Let's do it. Are they there? Yeah, they must be. People are talking. All right, let's go raid Spooky. All right, thank you everyone for tuning in. There's a double header this weekend. No condom, Chris. What's so funny? Oh wait, now you have to rate Brett on Rate My Professor. Wait, what? I'd say 5 out of 5 stars, man. That was one of the best lessons about fenwick trees I've ever had, for sure. Strike on, bro. JCast19, no condom, Chris. Have a good night. Thank you for tuning in. Low Road Sim Racing, Robodom, Q Ultimus. See you later, alligators. Rusty Hots, thank you very much for the follow, and see you next time. Brett1479, thank you so much. I really appreciate that lesson. I'm sure everyone here appreciates that lesson. Not only just that lesson, but all of the other contributions you've had throughout this channel's lifetime. DP Lopez from YouTube, adios amigo. Kim Sylvia, see you later. Everyone else, Slow Road Sim Racing, Strike on, bro. Am I saying names again? LeetCode, if you're still around. Bet Simp, Super Vaca Monk, adios. Obes, see you later. Demon, take care. And everyone else who I missed, see ya.